All right, well, we kind of rushed through this n-tree split up operation at the end of class last time, so let's pick up here again. So we were talking about the n-tree split up operation, and the example that we're doing is we're doing myTree.split up at position 2. And so if we look at part A of this figure, we see what's going to happen is the 60 is going to be split up. And then the 70 and the 10 will be the left child of 60, and the 90 and the 40 and the 20 will be a tree that is the right child of 60. So we went through this sequence of events that has to happen, this snapshot. So in part B, so I made a few inaccurate statements last time. In part B, we're not, as it says here in the caption, we are allocating new data and children vectors. We're not allocating a new tree. Okay, so we're allocating new data and children vectors. And so that little thing that looks like an empty tree is actually not a tree. It's a vector of data and it's a vector of children, both of which are empty. And then in part C, in a loop, now, and here's where in a loop you take these things a pair at a time, like the left child of 70 and 70 itself, and you append it to the new data and the new children. And then in part D, we take the 10 and the B, and we append that to the new children. So that's the other part of the loop. Okay, so that's the other part of the loop. And then, and now in part E, we remove C and append to new children. So if we look at part D, we see that C is the left child of 90, and when you remove it using the remove operation, the D, E, F, and G are going to be shifted over. All right, so that's the behavior of a remove operation in a vector. All right, so the D, E, F, and G got shifted over, and we put the C as the right child of 10. And now in F, this is where the two new trees are going to be allocated. So, so here's what's going to happen. The 60 is going to be this tree. So what happens in F, in part F of the figure, is you see my tree is going to have 60. Do you see what I'm saying? My tree is going to have one data item that's going to be the 60. So my tree is already allocated. We are mutating my tree. So the new trees that we have to allocate is we have to allocate the new trees for left and the new trees for right. And that's what happens in part F. And there a lot goes on in that part. So in F, that's where we allocate the two new trees. Okay? And then in G, what we do is we allocate a new vector for underscore data and we append 60. And we allocate a new vector for underscore children and we append left and then right. Okay? So that's where we modify the existing tree. That's the mutation of the existing tree. Okay? So, and then we did a little code walkthrough with this split up at. We saw the special case here, and then we saw part B, allocate new data and children vectors, remove and save 60. And then we looked at this in a loop, part C and D, in a loop remove 70, and in a loop remove 10. And then at the end of class last time, we were talking about, we looked at part E of the snapshot, remove C and append to new children at this. And then what we did right at the end of the class is we were looking at part F. Make a new tree for left with new data and new children, and a new tree for right with children data. And a new tree for right with current data and current children. And I don't know, I don't think I'm going to take the time to walk through every line of this code, but so so I think I'll let you, I don't want to take the time to work through all the details of this code. And then but the part that you are responsible for was the second part of part G. So the first part of part G is allocate a new vector for underscore data and append 60. So, so the way you allocate a new vector for underscore data is you do underscore data gets new vector t, and so that allocates a vector of data that's empty, and we append 60 to it by doing underscore data append root dat. where did root dat come from? Okay, yes, that was up here on the previous slide. T root dat gets underscore data error remove I. So this element, oh yes, and we even have a comment here. And this element would be at the new root. Right. Okay. And then data.append root dat. And then what you are responsible for, there's 2 lines of code here that you're responsible for doing the same kind of thing, but with children. Okay. So you'll have to do a new vector. You'll have to do allocate a new vector for underscore children. Okay. So it'll be. Do you see how to do that? It's mirrored. It's similar to what I've done here is I've done the code for you for the vector t part, but for the data, and you'll do the similar thing with the code for vector p for the children. Yeah. That is, yes. Yeah, so the question is, what's with the new vector t and then the empty parentheses? That's calling the constructor with no parameters for the vector. And what it does is it allocates a new empty vector. Yeah. Yeah, that's good. That's right. Now, let me say also that I've had some interesting debugging sessions with some of you guys. And this comes back to a comment that was made many weeks ago. The question was, when we introduced the concept, when we introduced you to the unit tests, do you remember this question? If it passed the unit test, does that mean it's correct? And what's the answer? No. What can any test ever show? It can only show the what? The existence of an error if it doesn't pass the unit test. But it can't show that, it doesn't prove that it's correct. And man, I'm telling you, there's some subtle bugs in some of you guys' vectors p and vector t's that passed the unit test, but with this use of vector t and vector p, they're not, there is a bug in them. And a common bug was not using t and p, but instead using int in vector t and vector p. You see what I'm saying? Because if you use int and then you test it where int is the actual type that gets passed, then it works. But these aren't ints. These are pointers to, these are n-way trees or pointers to children. See? So anyway, it's yeah. So check that. And I think I gave you the code for, I posted the code on Piazza for the vector t and vector p. So anyway, that cleared up a few bugs I've helped some people with. All right. So and then the other topic that we want to do that you need in order to do your homework for tonight is how to visit an n-way tree. I think there was it an in-order? I think you had to do an in-order, right? An in-order visitor. Okay, so now, so let's see how that works. Are there any questions about what we had just did? Okay, so look, so now here's where we're going with this. All right, what we're leading up to is a balanced B tree. In the same way that you have general binary trees, and then you have binary search trees, and then you have balanced binary search trees, which are special cases of general binary trees. In the same way, a B tree is going to be a special case of a general n-way tree. Do you see what I mean? And the only difference is how you do the insertions and how you do the deletions to keep the tree balanced. So what we're going to do is, this n tree is the host system for visitors. And what is all we need to do to make a B tree is we'll just have to do our insertions and our removals in such a way as to do what? Keep it balanced. Do you see? So there's really, after you've done this, the only code that you're going to need to do after this is just visiting, just implementing visitors. So here's our first way to visit. We're visiting a general n-way tree here. All right. So now, there are, when we did the by-tree CSV, what were the two cases that we had for the visitor? Do you remember? Remember when we did accept, what did you always have to implement when you did a by-tree CSV? Yes, we implemented the empty case and the non-empty case. Are you with me? So it was empty and non-empty. But now here's the thing. With a composite n-way tree, it's not just, we are not going to make that separation. We're not going to make that separation into empty and non-empty. It's just, there's just going to be one case. There's only going to be one visitor method, which is called case_at. And what you will have accessible to you in every situation is host and size, where size is the number of data items in the data vector. Do you see what I mean? And then you can tell, how can you tell whether it's empty or not? You can do a case on size inside your code. Do you see what we're saying there? How that's going to work? So accept only executes one visitor method, case_at, and the visitor has access to two parameters, host, which is usual, and size, which is, okay. So now let's do an example. Well, before we do an example, let's take a look at, this is the abstract n-tree visitor. So what are the two parameters that case_at has? A size and a what? And an entry, which is the host. And there's the constant version and the non-constant version. Are you with me? Okay. And take a look at what the accept method does. So now here is the code for the accept method. So now the accept method does this. Okay. All it does is it calls what? Visitor dot what? Case_at. So it doesn't do an empty case. It doesn't check to see if it's empty and do an empty case and then do a non-empty case, and so the plugin developer has to do one thing for the empty case and one thing for the non-empty case. It just does one thing. And what does it pass along? Underscore data, arrow, size, and star this to have access to the host. Are you with me? Does everybody see how that works? So now is all you have. So now what you can do is you can just use the size parameter that gets passed to know how many data items there are in the data in the data vector. And there's always going to be one more in the children vector if it's not empty. All right. So now we'll do. Oh yeah, question. Okay, yeah. Now this is the same. Passing star this, having the visitor pass star this is the same way that the host got passed in our binary tree, in our by-tree CSV. So star this is the host, and it is an n-way tree. And so what methods do you have access to? All those ones that are in the, split up, splice at, split up, split down. You have the getters. You have all the. Are you with me? So you have all those that you have, and host is an n-way tree. Yeah, and so you have all those. All right. So now let's take a look. So we'll do two examples. First we'll do root size, and then we'll give you some guidance on how to do the in order. So here's the root size visitor. So the root size, if the user wants to know how many elements are in the root, then we're going to write a little visitor method, and we're going to say, okay, you want to know how many elements are in the root? Well, here's a root size visitor. We'll program up this plugin for you. So precondition, this visitor has been accepted by a host tree. Postcondition, the size of the root of the host tree is returned. And the return size of an empty tree is 0. Okay? So that's the specification. All right? And so here is our root size visitor. Now look, is it void, yes or no? Here, is root size going to be void, yes or no? No, it's going to return an int. So with our visitor, what do we have? So what do we have to have for our visitor? We have to have an int result, private int underscore result, which is how many nodes are in the root. How many data values are in the root. Is everybody clear on this? And now this constructor, I'm not sure why I did the result gets -1. Didn't have to do that, but did it anyway for some unknown reason. And here, and so look, is all we have to do is implement one. We don't have to do an empty case and a non-empty case. Is all we have to do is do what? One case add. Are you with me? And look, this is super simple because the host is giving us the size, right? So all we do is what? Underscore result gets size, so that sets our attribute of the visitor. And because this is non-void, we have to have a little extra what? Little method? The little result method. So here's the result method, and that's the specifications which we saw on the initial slide. And as all we do is int result, return underscore result. And here is our global function for convenience. But now look, we've done this many times before. So what does this global function for, how does this global function for convenience work? Well, we have a little local visitor, entry root size viz is its type, and the name of the visitor is root size viz. And we do tree.accept root size viz. So accept takes a, what as a parameter? A visitor, like usual. Are you with me? And then we return, and then we use the return method of our visitor, and we say return root size viz dot result. Now, we've done this a number of times before. Does everybody see now the pattern? This is the same pattern that we've done many times before. All right? So that's, now what you need to do is, for your homework for tonight, is an in-order visitor. So let's recall how visitor pattern works in a binary tree. So we did so I have some slides here of the pre-order traversal for the binary tree CSV. Okay, so we'll compare this. We'll see how this one worked, and we'll compare it. And then we'll contrast it. We'll see how you have to modify it to make it work for the in-order visitor for a general n-way tree. So these slides now are from the binary tree CSV. So the bi-tree CS version of pre-order is void, so therefore the visitor version does not provide a result method. So this, you don't have you're not returning anything, right? When you do the pre-order, when you do the in-order traversal, you're not going to be returning anything, so we don't need that extra little result method. And the bi-tree CS version had an output parameter OS, and so the visitor version has this reference variable underscore OS. So this is the code. This is from way back in chapter 8. This is figure 8.44. So notice that we have OStream, a reference, an OStream reference, that's underscore OS, that's our input parameter. And in our constructor, OS is initialized to that input parameter. And now in the bi-tree CSV setup, we had to do two things, an empty case and a non-empty case, right? Well, here, in the empty case, we didn't do anything, and in the non-empty case, how did we do this is the pre-order. So what's the definition of pre-order? First do what? Visit the root, then do a what of the what? A pre-order of the left and a pre-order of the right. So here's the code. So OS stream host.root, because we had access to that root. And then what do we do? Host.left.accept star this. So we reused our visitor. We didn't allocate a new one, right? And then we do host.right.accept star this. So that's how we did the pre-order traversal for a binary tree. So now what's going to be different? Oh, and then we had this pre-order convenience function, okay, where we just set up our little local visitor and did tree.accept, okay? Now what's going to be different? How are we going to do an in-order traversal? Well, I haven't defined it yet, but I think you can see how it is. Check this out. So if this is like 70, 30, 60, 90, 20, and this is A, B, C, D, E, F. Now, What do you suppose the in-order traversal of this tree is going to be? What do you think? Yeah, so in general, what is, you're right. And so in general, what is it? You do it in, but when you say A, what you mean is do an in-order traversal of A. And then you do 70, and then you do a what? An in-order traversal of B, and then 30, and then an in-order traversal of C, and then 60, and an in-order traversal, all right? So what are you going to have to do? You're going to have to go through in a loop, right? But you got to be careful because there's how many children compared to how many data values? One extra. So in the loop, you're going to have to do the loop in pairs, right? C, you'll have to do it in pairs. You do the A and the 70, you do the B and the 30. You can either do it, it's one of two ways you can do it. You can, so you're going to have to go through in a loop. And in the loop, you're going to have to do the left one in this, and then the left one in this, and then the left one in this, and the left one in this, the left one in this. And then you'll have to do this one outside the loop. Or you could do it the other way around. You could do what? This one outside the loop at the first, and then you could do what? 70. This and this, this and this, this and this, this and this. Are you with me? And then it's a special case for what? The empty, because then you don't do anything. But there is no empty case, but on the other hand you have access to what? Size. To size. Are you with me? So you have to code that, so you code that case, that special case. All right? So so I have set up for you the OS stream ampersand OS, so that's the input parameter, and then the constructor initializes it just like we did in the B-Trees CS case. And here and this is kind of like the idiom. This is kind of like the pattern that all of these that you should use. I think it's easy just to adopt this pattern and just always use this pattern for your logic for doing these visitors. So look how it works. We have void case@, we have int size, entry host, and then that overrides. And then what do we have at the very top? What do we have? Switch size. And then you can do case 0, and then you can do default. And if you need to do case 1 as a special case, you can do case 0, case 1, and then default. You see what we're saying? You can do, that's kind of like the way to do it. So now instead of having a separate empty case that's polymorphically dispatched, we just do our own thing inside of the one. Yeah.
So the size and the
size is a parameter. Note that size is a parameter of case@, that is given to us by the accept, by executing accept, by having the host execute accept.
And so default is.
Oh, default is a C++, is the C++ feature of the case of the switch statement. Are you with me? Default is a C++ keyword. Okay. It is a feature of the C++ switch statement. And the way it works is if none of the cases are listed, you put a default, and that's what happens if none of the other cases are executed. Yeah.
So the 0 size?
Yes. Okay. That's the way the switch statement works in C++. Yeah. Does everybody, yeah, question?
I'm like that as well.
Okay, so the question is, could we have set up the binary tree, the B-tree CSV this way? And the answer is yes, we could have, but we would have lost our elegance of the polymorphic dispatch for the empty case and the non-empty case. You see, but we could have, you see what we're saying? But in this situation, that's not a big, that doesn't enter in so much. So that was a good question. That was a nice design. Yeah, because when these, and by the way, all this code is due to Gwen and Wong. And so that was a design decision that they made on how to set this all up. Yeah, but that was a good question. It was very insightful. Okay, now does everybody see how, I think some students were asking me about guidance on this one. Does everybody see now? Any more questions about how to do this? Are we good? And then here's the global function for convenience, and you need to set that one up, but you can model this after the other one, all right? I am really excited to present the Nguyen-Wong B-Tree on iTunes U for the first time. So we need to start, and by the way, the Gwen here is the Gwen that's, I think I mentioned this before, is the Gwen that is my co-author on the manuscript. He's at Rice University. Okay, so we need to start with some definitions now. So first of all, we need to define a B-tree. Now the B in B-tree means balanced. Okay, so a B-tree is an N-way tree, and we know what an N-way tree is now. We defined that earlier. So a B-tree is an N-way tree with the following characteristics. First, it is balanced. Second, it is ordered. And third, it has a node size restriction. Okay, so we're going to take this general N-way tree and we are going to impose these restrictions on it. So it is a general N-way tree with these additional things. So now let's take a look at each one of these in turn. First of all, what do we mean by a balanced N-way tree? So here's the definition of a balanced N-way tree. Now watch this, you guys. An empty N-way tree is balanced, and a non-empty N-way tree is balanced if and only if what? They all have the same height. Now, do you realize what that means? Like in general, everything has every child has the same height. In other words, if you had it like this would not be balanced. You see, because this child doesn't have the same height. See? Because these heights would be 0 and this height would be 1.
What the size of each vector is.
Doesn't matter. We're just defining balanced. What we mean by a balanced N-way tree is all the children are at the same height. All the leaves are at the same height. You can't have a short. You know how in a red-black tree, it was. Do you remember how in a red-black tree, what was the shortest one? Was what? Could be no shorter than the what? Than what? Or maybe the longest one. The longest one could not be longer than what?
Black height?
Yeah, there's black height. But what about the length of the?
Like twice as
Twice. Yeah, you're right. So it was the longest path to the leaf could not be more than twice the length of the shortest. You remember that? But it was allowed for there to be a little unbalanced. You see, it could be longer. It could be, they weren't all at but here, everything's on the same level. Now, as everybody see, for an N-way tree, we're going to enforce that. No more of these long things over at the end, and everything's going to be the same height. Are you with me? Okay, that's what it means for an N-way tree to be balanced. Okay, that's the first definition. Now, the next thing is, these are typically used for dictionaries, right? It can be used for dictionaries. And so what does it mean to be ordered? Well, check this out. Here's the definition of ordered. An empty N-way tree is ordered, so that's the base case. And a non-empty tree is ordered if and only if what? Now check out this tree first. If the data elements at root node X are in strict ascending order. So that means what? Boom, boom, boom. Here's the root. Here's the first one. This has to be strictly greater than this one. This has to be strictly greater than this one. So no duplicates. This is like a dictionary. Are you with me? Is everybody clear? So strictly ascending order. All right. And furthermore, all the data elements in x.child, so here, this one is tree X. This isn't like tree X. So all the data elements, so in x.child sub I are less than the values of x data. So what does that mean? It means all the elements in this child tree are less than what? This. All the elements in this, and all the elements in this child tree are what? Greater than this. Are you with me? Does everybody see what ordered means? It's just a generalization of what we had for it's the same idea, but it's just generalized. Okay? So these are all, and so these are all great. These are all greater than or equal to this one, and these are all what? Less than or equal to this one. These are all what? Greater than or equal to this one, and these are all what? Less than or equal to this one. These are all what? Greater than or equal to this one. And similarly all the way down. So when you do your in-order visitor, and you run your visitor on a B tree, what order will they come out in? Sorted. They will. Now they won't for a general, but they will for an ordered. Are you with me? Does everybody see how that works? Okay. So that's what it means to be ordered. Now, here's the thing about a B tree. So a B tree has all those characteristics, but now here's what makes it a B tree. A B tree is a balanced, ordered, n-way tree. So we've seen what that means. Balanced, all the same height, ordered, all this ordered. But what happens is there is a lower limit and an upper limit on the number of data values in a node. There's a lower limit and an upper limit on the data values of a node. So what happens is when you first allocate a B tree, you have to specify the order of the tree. You have to specify the order of the tree. And basically what happens is this. When you suppose you specify, let me just give you an example just to get the idea across for a first pass here. Suppose you specify that the tree is order 10. What you're saying is that a node can be as big as 10. It can have as many as 10 data values in the data part, but it cannot have fewer than what? Half that. So 5. So it'd be roughly from 5 to 10 data values in each node. Do you see what I'm saying? So you can't let the nodes get too empty on the one hand, and you also can't let them get too what? Too full on the other hand. You see? So they have to be in that range. It's a range of, half to full. They're filled. They have to be. It's like your gas tank. It's like your gas tank in your car. It's illegal for you to drive with less than half a tank of gas in your car. Your gas tank would have to be either half full or up to full. Half full or 3/4 full or full. See, a node, you see a data vector has to either what? Be half full or more. You see how that works? So the order of a Nguyen-Wong B-tree is the maximum number of data values in a node, but now there's an exception for the root. Because obviously, if you're starting to build a tree, and it's like order 10, the first item that you put in there has got to go in the root, and it's got to be less than 10, because you might not have be storing enough data values in the data structure to fill up the root node. See? So except for the root, the minimum number of data values is the floor of order divided by 2. So you remember the floor operation, the math floor? Remember this? What's the floor of 7 divided by 2? What's 7 divided by 2? 3.5. But the floor is what? 3. So if the order is 7, that means you can have from how many? Suppose the order is 7, the order of the B tree. Then you can have anywhere from what to what? From 3 to 7 data nodes, data values in the node. So here's some more examples. Oh, before we do some more examples, now let me make a comment about the Nguyen-Wong B-tree. Let's define the Nguyen-Wong B-tree. The Nguyen-Wong B-tree uses the composite pattern. And I'm here to tell you that I have never seen an implementation of the B-tree using the composite pattern. This is the first, to my knowledge, that this has ever been done. Okay? So that the child trees are B trees. And second of all, it uses the primitive operations of the N tree, of the N-way tree. Okay? And it uses the visitor pattern for insertions and deletions to maintain the B tree properties. And it uses a functional programming to pass a function as a parameter. So the Nguyen-Wong B-tree is a specific implementation of a general B-tree, and you'll find in the literature and in practice, most B-trees are implemented just with raw pointers, okay, or in a disk application, it's more complicated than that. All right. So this is here's what Gwen and Wong have done for the B-tree is what Sedgwick did for the red-black tree. What Sedgwick did for the red-black tree is there are general red-black trees, and remember when we did LL-RB tree, what was the LL? Left-leaning. So when you restrict it to being left-leaning, then it simplifies the code. Okay, so with the Nguyen-Wong and the way you do insertions and deletions is you go down recursively, and then you fix up on the way back. So that was a huge advance. So what Gwen and Wong have done is, for the B tree, it's the same idea. You restrict yourself to the use of these specific operations that maintain the invariant for a B tree, and you go down and you fix up on the way up for both insertions and deletions. It's amazingly simple compared to, it may seem complicated when we go through it, but as with the red-black tree, it's amazingly simple compared to the general unrestricted B tree. So it is a specific implementation of a B tree. All right. So now let's do some examples of what the order means. So first of all, so here we have, if you have an order 4 Nguyen-Wong B-tree, then every node has, so what's 4 divided by 2? That's 2. So it has from 2 to 4 nodes. And if it's order 5, then it has from 2 to 5 nodes, and if it's order 6, it has from 3 to 6 data values. Now always there's one more child than there are data, right? But just remember that the order is the maximum number of data values in a tree. Now this definition of the order of a tree is not the standard definition, but Gwen and Wong have adopted this definition for their implementation of the tree, and I think it's easier to deal with than the conventional definition. All right? The order of a tree. So the order of a tree, of a Nguyen-Wong B-tree, is the maximum number of data values in each node, and always with the exception of the root. Is everybody clear on this? Yeah, question?
So at all times after you've inserted and fixed up and all that, at all times your tree is ordered and balanced.
At all times, not only is it ordered and balanced, but it also follows the node restrictions of how many elements are in each node, how many data values are in each node. All 3. Yes, definitely the first 2, but also the third. That was a good question. Is everybody clear on that? Yeah, and so as we do these operations, we're going to have to maintain these invariants. We'll see how these invariants get maintained. This, I tell you, when I first saw this, I couldn't believe it. Now, here's the thing, you guys. The insertion and the removal the insertion and the removal algorithms for the Nguyen-Wong B-tree are pretty complex. The C++ code is pretty complicated to implement. It's fairly detailed, and we don't have time to go over all the ins and outs, and I don't even think it would be beneficial if we did. So here's our plan. Here's what we're going to do with this project. All you are going to do is I will give you a pseudocode description of the insertion and the removal. And what we will do is we are going to go over and we are going to see how insertion and removal works in a Nguyen-Wong B-tree, but you won't have to implement any of the code. The code that you are implementing tonight for the what was it, splice at, split up and split down, those are all operations that are used by the insertion and deletion. So if that code works, then your code for the Nguyen-Wong B-tree will work, because I'm giving you all the code for the insertion and the removal for the tree. On the other hand, knowing what a balanced a B-tree is, this is your assignment for the Nguyen-Wong B-Tree, for the B-Tree project. And basically they are just visitors to do these operations. And actually, now that we know what a B-tree is, we can see how to. So first of all, contains. How are you going to do contains? How will you write the contains visitor? How will you know? How will you know if it contains? What will you do? You'll have to do what?
Is
If it's between there.
Go through in a loop. Go through in a loop, and if the key that you're looking for is what?
less.
Is bigger than this, you got to go to here. If it's bigger than this, you got to go here. And then finally, you got to find, you either find it here or you find what?
Or you go down.
Or you go down and you repeat it here. But you don't have to do the whole tree. It's kind of like doing a binary search, but it's an n-way search. You see what I'm saying? You don't search the whole tree, you just boom, boom, boom. Now, does everybody see how that works? So knowing the structure of a B tree, yeah, now you can do the contains visitor. So the NWB tree project basically just uses the general n-way tree, and it has visitors for the insertion and removal to maintain those invariants. Are you with me? And then height, how are you going to look at how are you going to find the height of this? You only have to go down what?
One.
Just one until you get to the bottom, because you know they're all the same height. Yeah. And what about is empty? You only just got to check this. What about max viz? What about how are you going to find the max? Where's the max? Boom, 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 boom. Where's the min? Boom, 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 boom. What's the number of nodes?
Number of children.
Well, no. This one plus however many, boom, 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 and then how many? But see, it's the composite pattern. So what can you do? Just reuse your visitor and boom, boom, boom. And how many values? Now, how many nodes would this one have? 1, 2, 3, 4, 5. But how many values? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now I think you know all there is to know to do your Nguyen-Wong B-Tree project, because, like I say, the code for the insertion and removal is complex, and we will trace through how it works. But you're ready to go for this project as well. Now, is everybody? Are we good? All right. See you next time.